Hi everyone, my name is Thomas Kim. Today is May 3rd, 2020. This is my 28th episode about the programming language C++ training standard. In this episode, I will discuss low-level C++ programming, fast multiplication, fast exponentiation, fast modular exponentiation. The purpose of this episode is to motivate my audience to learn assembler language. I learned the assembler language for 2 years, over 25 years ago, while I was in college. Since then, I never used the assembler language, and I forgot most of the CPU instructions. But still, I remember low-level bitwise operations, which enable me to create more powerful C++ algorithm. We may never create our programs in assembler language, but understanding some level of assembler language helps us better understand modern C++ language. Let me fix my wording here, but still I remember lower level bitwise operations, which enables me to create more powerful C++ algorithms. We may never create our programs in assembler language, but understanding some level of the assembler language helps us better understand modern C++ language. A couple of years ago, I created complete RSA algorithm in C++ language from scratch. If you are interested in RSA algorithm, please double-click this link. In this video, I demonstrated how to use my RSA algorithm. To implement RSA algorithm from scratch, we need to implement 3 fundamental algorithms. Algorithm for manipulating prime numbers, Euclidean algorithm, and extended Euclidean algorithm. Third, we need fast modular exponentiation algorithm. We use bitwise operation all the time. For example, in episode 42, how to set thread affinity, how to retrieve processor configuration. In this video, I use bitwise operation to retrieve processor configuration. Also, fast modular powering algorithm using Fermat's and Euler's theorem. In this video, I used bitwise operation. Also, in episode 24, must-know C++ training function is constant evaluated. In this video, I implemented a power function using bitwise operation. In this episode, I promised I will film videos about bitwise operation. So, bitwise operations play very important role in C++ programming. The question is how we can learn advanced bitwise operations. Well, most C and C++ books do not deal with bitwise operations. If you want to learn advanced bitwise operations, you have to learn assembler programming language. The answer is learn the assembler programming language. I will not film videos about the assembler language because I forgot the CPU instruction sets And secondly, I don't use assembler language in C++ programming. I only use the techniques I learned while learning assembler language. By the time you watch this video, you can double-click this link and download the complete source code. Without further ado, let's get started. Start Visual Studio Code. Open your working folder. Select empty space. Click this button. 028 Fast Exponentiation. Hit enter. Click this button. Bitwise.cpp. Hit enter. Ctrl B. Include talk play fun. Output HPP. Talk play fun. S stream auto and L talk play fun and L. Void test shift left operation. int main. I hate copy and paste source code in my video, but in this session I will copy and paste some code that I created long ago. I will paste it here. Now I will copy this function in the function main. Here character C -3 unsigned, character U is C, stream signed, tab 3 tab characters, unsigned, and there. Now we display character C and unsigned character U like this. Stream, we need a typecast short C colon to string C to tab short U colon to string U and there. Please note that we defined toString here. It converts integral type to string. Now start command prompt. dir cd 028 fast exponentiation clehsc sdd c++17 bitwise.cpp fe n.exe. Hit enter. Sorry. T. We build again. CLSM. I will remove one T here. Build again. CLSM. Okay, it looks good. In this code, character C is -3. U is unsigned character C. toString converts character C to binary string. So minus number in binary format looks like this. Unsigned character 253 in binary digit looks like this. So in binary digit, they look the same. In case of U is interpreted as unsigned character. In case of character C is interpreted as signed. So binary representations are identical. But when it comes to ShiftLeft bitwise operation, there is a huge difference between signed and unsigned integral types. Now here, C ShiftLeft 1 bit, U ShiftLeft 1 bit, ShiftLeft bitwise 1 bit. Now I copy this statement, paste it here. I will rearrange like this. Now we build again CLSM. Please pay attention to most significant bit. Most significant bit. Most significant bit. Most significant bit. In case of signed integral type, for negative number, most significant bit, binary number 1, is faded. In case of unsigned integral type, most significant bit, most significant binary bit, 0 is faded. So the remainder and the remainder are the same. But most significant bit in case of signed is 1. In case of unsigned, most significant bit is 0. This is a huge difference, and we should never forget this fact. In the ShiftLeft bitwise operation, in case of negative signed integral values, binary digit 1 is faded to the most significant digit. In case of unsigned integral values, binary digit 0 is faded to the most significant digit. Sorry, it should be most significant bit. Most significant bit or binary digit. This fact has a huge impact over bitwise operation, as you will see shortly. Now scroll down. Here I make demarcation int identity int p. Here unsigned u p. Int p equals 0. 0 is additive identity and p is return value. Int a equals 1. While u, it means u is not 0, then you shift 1 to the left. Shift left 1 bit. Now a plus equal a. If u bitwise and 1, then b plus equal a. I will explain this identity function shortly, so please bear with me for the time being. We will learn how to use this identity function first. Then I will explain this part of code. Void test identity. Now int p minus 3 stream p equal identity p, and there. Now copy this function name, copy, paste it here. I will disable it. We build again CLSM. So minus 3 is minus 3. This identity function returns identity. Now I will disable this part. Instead, intu p. Now we build again CLSM. it does not end. It is in endless loop. Control C. So it does not work. In the function test identity, we assigned negative number 3 to integral type p. So we are calling identity function this function. If u is negative number of type int signed integral type, u can never be 0 by ShiftLeft bitwise operation. Using ShiftLeft bitwise operation, u can never be 0 when u is negative signed integral type. That's why when we use bitwise shift operation, we have to use unsigned integral type. Now I copy this function, copy, and I make demarcation here, paste. I will rename fast multiplication, and here void test fast multiplication. Copy the function name, paste it here. I will disable it. I have to remove closing parentheses here. Now I will copy this part, cut, paste it here, and fix like this. Now here INTA equals 5, INTP equals -2. Stream A times P equals, we are calling this function, paste A P, and there. This function returns A times P. Now we build again. CLS M. So 5 times -2 is -10. Once again, if I disable it, enable it, this function does not work. It does not work. It falls into endless loop. Control C. Now I will re-enable it, disable it. Now we can try with a positive number 3. 5 times 3. We build again CLS M. So in this function, we use bitwise shift and addition, but we created fast multiplication function. Now I copy from here up to this point, copy, paste it here. I will name it fast power. Now it returns A power P, or A times A times A, like this. Now B should be 1. 1 is multiplicative identity. Now it should be multiplication. It should be multiplication. I will copy this function name, paste it here. Now I will copy this function name, paste it here. Copy this function name, copy, paste it here. Now 2, 3. We fix our code like this. In the command prompt once again, CLS-M. So 2 to the power 3 is 8. For example, 5. If we build again CLS-M, it works perfectly. 5 times 5 times 5, 125. In our previous episode 24, must know C++20 function is constant evaluated. In this video, I implemented POW power function using left shift bitwise operation. So I will copy the link and paste it here for your reference. Now copy this function from here up to this point. Copy. I will make demarcation, paste. Now it should be past modulo exponentiation. Now it returns a power p mod n int n. Now here b modulo n a modulo n. I will copy the function name, copy, paste it here. Now int n 37, we pass 37, it can be 335. Now I fix this part, mod n. We call this function here. Now I copy this function name, copy, paste it here. Now we build again CLS-M. So 3 to the power 35 mod 37 is 25. For example, 3 to the power 2, 7. We build again CLS-M. 3 to the power 2 is 9. 9 mod 7 is 2. So this past modular exponentiation function works perfectly. In this video, fast modular powering algorithm using Fermat's and Euler theorem. In this video, I explained how to implement fast powering algorithm. I will copy this link and paste it here for your reference. This fast modular exponentiation algorithm is very important for RSA algorithm. So, fast modular exponentiation algorithm. If you understand this identity function, you understand all these algorithms. You can understand fast multiplication, fast power, and fast modular exponentiation. I highly recommend you to watch this video. Control-click, open. In this video, I give more in-depth explanation. Also, I will create a folder identity.cpp, hit enter, and control home. I will copy up to this point, copy, paste, int main, call this function, paste it here, and print out the values of A, the values of B, like this. For example, stream A, stream A, stream, and there. Don't forget and there. If you don't flush to console with and there, you cannot see anything. In the command prompt, identity, hit enter, CLS M. Something wrong. It should be number 3. CLS M. So the value of A, 1, 2 is added. I will disable this part. We build again. 116. I forgot semicolon here. CLS M. So if it becomes, for example, 5, 1 plus 4 becomes 5. For example, 7, CLS M. 1, 2, 4 is added together and makes 7. By experimenting this identity function, you can completely understand this algorithm. I think I can create at least 10 or 20 or more videos about bitwise operation, but we have many more important things to cover. Please subscribe to my YouTube channel. Thank you for watching.